So I will be giving you like a very quick teaser. So this presentation is meant to be like at most 15 minutes, maybe 10, about our very recent work on basically how to combine the ideas that made Maxent into deep SDM approaches to make them work better. So this is work with all of these people on the bottom. So many of them are in the, is Maxime here? So the first author didn't arrive. But this is like also with Christophe Botella, with Maximilien Sergent, Pierre Bonnet, and Alexis Joly that are all here. And I will give this presentation from like my own very biased perspective. So I want to like thank all of the co-authors and also apologize for the presentation. So I think, I mean, there is no discussion now, like everyone knows that in many fields, deep learning has made like a massive difference, right? A lot of people show graphs like this where you see, okay, like this is the error in the ImageNet challenge that was decreasing very slowly at certain rates, and then bump, deep learning came, and there was like a big bump in performance, and then it continued faster than it was advancing before. So like deep learning made like a massive difference for this particular task. And we tend to be under the impression that then this should apply everywhere, right? But everywhere, right? Like I would argue that so if we look at, for instance, like the GeoLife Clay challenge. So this is like the leaderboard from last year. If we look more in detail at the leaderboard. So we would, so the top one, so it's not true that they didn't use deep learning, so they built like an ensemble that includes the baseline provided by the organizers that uses deep learning, but all of their development, and whichever it is that makes the difference with respect to the rest, there was no deep learning involved, right? There was like a lot of tricks, a lot of heuristics, a lot of different techniques that improved the results, but they didn't work at all on the deep learning models or make them better, right? So I would argue that it was not really deep learning that made a difference in this particular challenge that involves SDMs with satellite data and so on. Another example is something that we saw before in a presentation from Davis. So in the result of this paper that is very recent, it was very clear that okay, this is not very visible. But the first results are some deep learning results, let's say old ones, like 2023, right? So like pretty recent. Then these are the results that they achieved with also like a deep learning approaches, like playing around with how to use the pseudo absences. And yes, they improved with respect to the previous deep learning state of the art, but they were still behind Maxent, for instance, like single species models that don't use any deep learning at all. Right, so this is on a data set that was, we also saw before, by Jane Ellis and others, where there is no remote sensing data in this, right? So there's only like tabular data. And in a way, like so deep learning didn't bring an advantage here. Like the feature extraction capabilities of deep learning just didn't play a big role in this data set either. And it seemed that we would be better off using like traditional non-deep learning approaches. So what are the main differences, right, between, in this case, Maxent and the classical deep learning approaches that we apply for deep SDMs? So the objective is the same, right? In both, we want to understand the niche of the different species. The features, like in the case of Maxent, they are sort of predefined, right? There's like a list of features that we will extract from the environmental variables, and in deep learning they are learned. So probably I would argue that it's not that makes the advantage of Maxent. If you look at the losses used in Maxent and in the majority of deep learning approaches in deep SDMs, so this is like, well, we're not seeing much, But so these two equations come directly from the Maxent paper. The first one we can see that is how to compute the scores, and it's basically softmax. So this z, the partition function, is basically designed to be exactly a softmax, so that the whole thing sums to 1. Then on the top we have the exponential of some logits, exactly like we do in deep learning. So this is basically the same thing that is done in most classification-style deep learning approaches for SDMs. And then on the bottom we have the loss itself, which, okay, we try to maximize the likelihood of the observations, and there is some regularization. These are also the things that usually people would do in a deep SDM model. Maybe there is a difference that in the case of deep learning models, the loss is computed batch-wise, and in Maxent, usually you would compute it for the whole data set at once. If it makes a difference or not, I think this is, for me, not super clear. But there is a big difference. And is that in deep SDMs, usually, like this softmax is computed per site across species, but in Maxent is computed across sites. So in Maxent, basically what we're trying to model is the probability, so given a species, the probability of selecting one site given the environment of all sites, while in the classical cross-entropy based deep learning approaches that are the ones that are mostly used, it would be the probability of finding a species in a site given the environment of that particular site. So even though it looks very similar, in the end it's like two very different objectives that the two types of approaches are seeking, right? And in the case of binary cross-entropy, is very similar, except that the probability is not relative between species, but just the absolute probability of one species being present. So in the end, what we tried is that we have a batch of samples. Let's give it to our deep learning model, and instead of running the softmax for every row, so for every site, let's run the softmax for every species across the batch, right? Across the sites in our batch. That's basically the main difference between what we did and the classical deep SDM approach. And so these were the results in AUC on previous models on this data set by Jane Ellis and others. And so there we can see that the best results are basically Maxent using target group background. So basically the pseudo absences are only sampled from locations where other species have been observed. And so these are all the models that we run with different losses. And we consistently observe that with the approach that I described, which is literally you take cross entropy and you reverse the softmax, so you do the softmax in the other dimension, we consistently obtained better results than Maxent. And because it's a deep learning approach, we can also apply this to maybe data sets where you wouldn't apply Maxent. Like in this case, we applied it to GeoPlant, where among other data sources, we have time series coming from Landsat. And what we saw is that in both, so we basically run it with bioclimatic variables, and we run it with the Landsat time series. So the bioclimatic variables, we run it so we can actually compare it with Maxent. And we observed that in this case, it also outperforms Maxent. And in the case of the land cover, the Landsat time series, then the DeepMaxent approach also outperforms the other deep learning losses that we tested that are commonly used. And so depending on which is your perspective, then I would say that so you could see that what we have done is basically like made Maxent features learnable with a neural network, or maybe like made deep learning models more suitable for SDMs by applying the principles of Maxent. And in general, we saw that we obtained with this approach results that are better than classical deep learning losses and better than classical Maxent, but only as long as target group background is used. So if we use like just random points for the pseudo absences, we don't really obtain an advantage. And so we haven't explored other sampling strategies, which is maybe something that is worth doing in the future. And thanks a lot. This was my presentation.
Any question on DeepMaxent?
Thank you for your presentation. I was wondering, you started your presentation by showing that for the GeoClef change, it was not deep learning that was winning the change. And I was wondering if you tried, or are you planning to try the DeepMaxent on the change to see if in the end it's still traditional machine learning winning, or if
So GeoPlant is actually like it's basically a GeoLifeClay 24.
Okay, sorry.
So we tried in one subset of the variables. We didn't try with all of the modalities, but we tried with the bioclimatic variables, and we tried with the time series, and in both cases we worked better. So but we didn't try with the whole set of variables yet.
Okay.
Maybe something to specify is that DeepMaxent was more designed for training on PO data, presence-only data. But in GeoLifeClay, people were using a lot the presence-absence data.
Excuse me, I'm sorry, but you don't speak in the microphone.
Yes. So what? He has the microphone.
Go for it.
Oh,
Okay. I was just saying that the experiments made on DeepMaxent were made by training models on presence-only data and evaluating on presence-absence. But in GeoLifeClay, most people used presence-absence data for training, so giving some advantage in this data context. That makes the comparison. Basically, in GeoLifeClay, there was very few approaches based on presence-only data because it was difficult to deal with it.
So I wanted to ask, in the statistical SDM literature, there was this long discussion of Maxent, if the Maxent loss is basically a Poisson regression, where you then adjusted background, and I was seeing that you also had the Poisson loss always calculated, but also not identical to the Maxent. So is this due to your pseudo-absence sampling, that it's not completely random? But if you have completely random pseudo-absence sampling, you should get the same loss as a Poisson.
So Christophe will correct me again, right? But no, like in the end. So if I understood it well, like so Maxent still has like this this partition function there that is not there in Poisson, right? There's this normalization to make sure that the sort of the probabilities across sites sum to 1. Right, and this, so in principle, so in theory, the minimizer should be the same for both the Poisson and Maxent. In practice, like so the optimization path will be different, and it reaches different results. Okay. And systematically, with this so the normalization sort of improves the Poisson results. So in that sense, like DeepMaxent is like a normalized version of Poisson. Should get to the same result like if you have like infinite data and so on, right? And you have like infinite batches, but in practice it reaches better results.
Okay.
Thanks for the talk. So if I understood this right, the the tweak that you did was changing the loss in the sense that it optimizes across species rather than across sites. And that perfectly makes sense that you, like if you have this one-by-one training of the classical approach, you have very much this site-based perspective. But I guess there is also a trade-off involved, right? I mean, we have been talking repeatedly about the edge that these deep SDMs have in predicting community composition, and I would assume you lose that to some extent, but perhaps not entirely because you still have one model and you have shared weights for different species. Have you done any evaluation of that? You know, flipping the exercise around and comparing Maxent with deep SDMs in the site-wise comparison rather than the species-wise, for example, and seeing which one is best across both perspectives?
Yeah, so we haven't. I mean, it's a very interesting question. Like one thing would be, so what happens if at inference time then you swap again the softmax, right? Because indeed it learns like a common representation for all species. In principle, it doesn't. So you don't inform the model about like prevalence per site or like relative abundance or anything like this, because it really only compares site with site, not species with species in the same site. So I would assume that it will perform less well for modeling communities, I guess, but we haven't tested this.
Thanks.
Thank you, Philippe. Okay, next speaker. Should we go?